Thank you for Chairman. I work for Kobelco Research Institute. I'm in charge of CAE and Evaluation Department. Today, I'd like to talk about applicability of modified ritchie knot-lise failure criterion to predict the onset of cleavage fracture for the test specimen with residual stress introduced to the crack tip. Fracture toughness has been known to increase apparently by preload at high temperature region than the cleavage fracture temperature region. It's called warm pre-stressing effect. Conventionally, the global approach had been used to evaluate the influence of preload. On the other hand, the local approach has been used recently. Variable stress is one of the widely accepted methods. However, recent research suggests that the variable stress approach is not without its limitations. For example, recent research have reported that the variable parameter vary with size and temperature, and calibration variable stress requires many specimens. We first sought to re-examine Chen et al.'s opinion that it is necessary to distinguish the concepts of the minimum toughness or the lower boundary of toughness value from that of the scatter band of toughness. The former is a definite parameter determined by specimen geometry and yielding properties, and the latter is statistical behavior determined by the distribution of the weakest constituent. We interpreted Chen's opinion as meaning that a minimum JC can be reproduced by running an elastic plastic finite element analysis EPFEA with a given stress strain curve and a failure criterion. For the failure criterion, we consider one of a modified ritchie knot-lise RKR failure criterion, that is a 4 delta D sigma 2 to C criterion, which predicts the onset of cleavage fracture when the crack opening stress sigma 2 measured at distance from the crack tip equal to 4 times the crack tip opening displacement CTOD delta T, hereinafter denoted as sigma 2D, exceeds our critical value sigma 2C. This criterion was validated as explaining the crack depth dependence on JC by Dodds et al. And test specimen thickness effect on JC by Meshi. Through examination of the applicability of the 4 delta T sigma 2 to C criterion to decommissioned RPV steel JC database with specimen thickness ranging from 8 to 254 millimeter, Meshi showed that although the variation of JC was very large, and the variation of sigma 2 to C was very small, approximately 4%. Thus, we reached the idea that the convergence for convergence of sigma 2 to d for increasing load is necessary for fracture initiation because critical value sigma 2 to c is equal to the converged value of sigma 2 to d. If so, sigma 2 to d can be calculated by EPFEA with a given stress strain curve without a conductivity fracture toughness test. Thus, we thought that the JC of specimen with residual stress might be predicted without JC that data with applied residual stress. Also, we expected that a minimum J corresponding to sigma 2 to D equals sigma 2 to C, denoted as JS, would give an engineering prediction of the lower bound of fracture toughness. This study is intended to examine the validity of method for predicting JS corresponding to sigma 2 to D equals sigma 2 to C for specimen with residual stress by preload. 0.45% carbon steel, GIS S45C was selected for examination. Sharpie impact test results and true stress true strain curve obtained from tensile test are shown in these figures. From Sharpie impact test results, -10 centigrade was selected for EPFEA. FEA model and material properties are shown on this page. SCB specimen with a rectangular cross-section of width W equal 46 mm was considered for examination. Load conditions are summarized on this page. First, preload was increased to 33 kN at room temperature. Then after preload was unloaded, the temperature was changed to -10 centigrade. And then load was increased to the predicted the value of predicted fracture load. Material parameter were used the property for temperature for each process. Abacus was used as FEA solver. The FEA-J denoted that JFEA was evaluated using the relationship between load and crack mouth opening displacement based on ASTME 1921. The CTOD was calculated by a means of 90 degrees intercept method. Since it is necessary to determine the converged value of sigma 2 to D to predict JS, but there is not definite method to determine the converged value of sigma 2 to D. Here we applied the following method. First, the dataset of sigma 2 to D and JFEA was fitted with this function. Then J at the value of a normalized sigma 2 to D over a converged value alpha 1 plus alpha 2 plus initial sigma 2 to D. It is equal to 0.95 was defined as JS. The relationship between sigma 2 to D and JFEA is shown in this figure. For this figure, sigma 2 to D showed converging tendency for increasing JFEA as expected. By using a method for predicting JS, the value of JS was predicted 18.9 Newton per millimeter. And next, we performed the fracture toughness test to examine the validity of this method. First, fatigue pre-crack length 2 mm was inserted to the specimen at room temperature. Then after the residual stress was introduced to the crack tip in the same way as EPFEA, the temperature was changed to -10 centigrade. The fracture toughness test was conducted in accordance with ASTM 1921. JC are compared with the predicted JS together with the master curve 2% tolerance bound value as shown in this figure. JC is calculated by EPFEA at fracture load on test. For this figure, we see that the fracture always occurred after sigma 2 to D reached sigma 2 to C, and the predicted JS was conservative compared with JC and close to the 2% tolerance bound. Thus, it was concluded that the modified RKR failure criterion is applicable to SEB specimen with residual stress. In addition, the validity of the method for predicting JS was confirmed. The success in current work indicates that the JS for a given specimen and temperature can be predicted with the stress-strain curve. And the fracture toughness test without a residual stress may not be always necessary to predict the JS. The conclusions of my talk are summarized as shown here. Thank you for your close attention.